Hi everyone, welcome back to the Solver Deep Dive series. This is an ongoing series where I explain different components of MILP and CPSAT solvers. And in today's episode, we are going to discuss LNS in CPSAT. So LNS is a very successful heuristic in the OR tools CPSAT solver. So we are going to deep dive into how the LNS workers are scheduled, what are the different types of neighborhood generators, and how this LNS adapts some of its parameter based on whether it is successful or not. So previously I also covered adaptive large neighborhood search in MILP, which is a paper by Gregor in the Reading Club series. So you might want to take a look at that. Although I don't think this video depends on it. It's not a prerequisite for this video, but you might want to watch those videos that will give you some better context. Right, so let's get started. Okay, so before we jump into the LNS itself, let's take a look at the architecture of the solver. Right, so CPSAT solver, we mostly trigger with multiple threads, and there is one active worker per thread. So let's call it a subsolver. In the CPSAT solver, we have multiple categories of this subsolver, but to simplify things, I'm going to talk about two of them. So let's call it full and re-enter. So the main difference between these two categories is that the full subsolvers will permanently occupy the thread, whereas the re-entering type of subsolvers will give back the control. So what do I mean by that? Let's say I have one thread that is assigned to max LP. Then throughout the solving process, for that thread, only max LP will be active. So that is not true for re-entering type of subsolvers. So LNS falls under this re-entering type of subsolvers where they solve subproblems. So since it's a subproblem, one LNS subsolver is only active for a part of the full solving time. So there are many subsolvers inside the LNS categories. There is one per neighborhood generator. We will take a look at the different neighborhood generators later in this video. So feasibility jump will also fall inside this kind of re-entering type of subsolvers. So how this works is that there is a scheduling process for all of these re-entering type of subsolvers. So let's say one LNS is scheduled, then it will start with generating its neighborhood. It will solve the subproblem and then it will give back the control. And then the solver will decide which subsolver to schedule next. So how do we decide which subsolver to schedule next? So that is done by using this kind of a score formula. So what is this score? So it is multiplying three quantities. So one is how many tasks are scheduled for that particular type of subsolver. So it's, let's say, one particular type of LNS. How much time is spent on an average for that particular type of subsolver, and what is the confidence factor? So the confidence factor is 1 if we have already finished 10 tasks, but otherwise if we haven't finished at least 10 tasks, then the confidence factor is this one, which is e raised to how many tasks are scheduled and how many tasks are finished, which is number of total in-flight tasks. So this score formula is essentially trying to balance the time across these different types of subsolvers. So one of them is taking too much time, then it will be scheduled less often, whereas the one that is, let's say, very, very fast, then it will be scheduled more often. So if you notice that here we don't care about whether these re-entrant subsolvers are successful or not. So whether they are finding feasible solutions or whether they are improving the current bounds or whether they are improving the current solutions or not, all of this we don't care about here. Here we only care about how much time they are spending in this subsolve process. So whether an LNS subsolver is successful or not, it's a very important information, but it is taken care of inside the LNS. So we will take a look at how. But before that, we will take a look at different types of neighborhood generator. So there is one LNS subsolver per neighborhood generator. In the CPSAT solver, there are many types of neighborhood generators. So I'm broadly categorizing them into these 4 categories. So in the generic category, we have 2 neighborhood generators. They don't depend on the problem structure, therefore they are called generic. This one basically randomly relaxes a bunch of variables from a given solution, and then the other variables are fixed to that solution value that we are looking at, and that's the neighborhood. This one is also doing random relaxation of variables, but it is going one constraint at a time. So it will randomly pick one constraint, relax all the variables in that constraint, and move on to the next constraint. So next we have the graph category. So here we have three neighborhood generators: variable graph neighborhood generator, constraint graph neighborhood generator, and arc graph for neighborhood generator. So here the graph is between variables. Okay, so the two variables are connected if they share a constraint. Here the graph is between constraint and variables. So there is an edge if one particular constraint contains a particular variable. Okay, and this one will come to it later. So in this variable graph neighborhood generator, we start with picking one variable and then do a breadth first search. So what does that mean? It relaxes that picked variable and then add in the queue all the variables that are connected to it. And the process is kind of similar for this constraint graph neighborhood generator. It will start with picking one random constraint and relax all the variables inside that constraint. And then it will look at what are the connected constraints. So the variables that are relaxed, which other constraint those variables appear into. And then one by one, they will also start relaxing those variables in those constraints. So these two are doing a breadth first search, but this one is different, right? So this one is doing a random walk. Okay, so what does this look like? So it will start with one variable and then it will look at what all constraint that variable appears in. So from that, it will pick another variable which appears in one of those constraints, and it will continue the process like this. Right? So it is basically taking a random walk in that graph. The next category is problem specific neighborhood generators. So I don't have much expertise in these different types of problem, which is scheduling problems, packing problems, or routing problems, but there are specific neighborhood generators for this type of problem. So for example, for scheduling, there is a scheduling time window neighborhood generator or random interval scheduling neighborhood generator. So obviously this scheduling type of problems, they involve a specific type of constraint. So there are interval constraints and there is no overlap constraints, and those kind of constraints are present in this kind of problems. So for packing, there is random rectangles packing neighborhood generator and slice packing neighborhood generator. For routing, there is one routing random neighborhood generator and routing path neighborhood generator. So this kind of neighborhood generators are specific to a problem. So if those kind of constraints are present in the problem, only then these neighborhood generators are activated. And the last category is solution induced neighborhood generator. So rinse and rents basically fall into this category of neighborhood generators. So I'm not going to explain rinse and rents in detail in this video. I have explained that in detail in previous LNS video. So you can take a look at that. But briefly, I can quickly say that rinse is basically trying to combine an incumbent solution with an LP solution. So whereas rinse starts with an LP solution and restricts the bounds of variables based on that LP solution. Okay, so now we will take a look at the adaptive parts of these neighborhood generators. So one of them is the deterministic time limit and the other one is difficulty. So think of this as the normal time limit, but it is rather dependent on how many instructions are executed inside the solver. Okay, so how is this adapted? So we measure the number of non-improving calls to this neighborhood generator, and if this number of non-improving calls is greater than, let's say, this specific bump value, then we increase this time limit by 2%. So it is capped by this maximum number, which is 60. So here the bump value is also not fixed. So every time we hit this condition where the number of non-improving calls are bigger than B, then we increment this B value as well by 50. Right? So overall, this depends on how many times I call this LNS and how many of those times it did not improve the current solution. And the other adaptive parameter is difficulty. So difficulty basically determines how many variables will be fixed. So it's a number between 0 and 1. So 1 means all variables are relaxed, which basically means extremely difficult problem. On the other hand, 0 means none of the variables are relaxed, all the variables are fixed. That means an extremely easy problem. So this is how it is adjusted. So if the solver returns with this status, which is optimal or infeasible, that means within the given time limit and resource limit, it managed to completely solve the sub problem. Then we need to increment this difficulty. And if the solver returns feasible or unknown, that means the solving process is not yet finished, which basically means the difficulty is higher than we need it to be, and therefore we need to decrease the difficulty. So let's take a look at how this difficulty is adjusted exactly. So unlike the time limit, this is a bit complicated case because here we need to make sure that this number stays between 0 and 1. Right, so at the beginning of the problem, we don't know where the difficulty should be. So we will always start with 0.5. So initially we want it to move fast, but as the solving progresses, we want it to converge to a specific value. So this is how it is updated. Let's say the current value for this difficulty parameter is V. Then this is how we will calculate a factor. So the factor is 1 plus 1 divided by square root of total number of changes plus 1. Plus 1 is obviously preventing things from dividing by 0. The C in the denominator, the total number of changes in the denominator, basically makes sure that this thing converges to 1. So initially this C will be 0. That means this factor will be very large. As we make more and more changes, increments or decrements, this factor will become smaller and smaller. So notice that this factor is always greater than 1. So V times factor will always increment the value, and V divided by this factor will always decrement this value. Right, so here we have this problem that if we just increment it this way, then there is a chance that we will go out of this one bound. So how do we prevent it? So let's say we are somewhere over here. So if you want to increment it from here, then there are two ways. So one is we can multiply it by this factor f, and the other way is slightly more interesting, which is we first take the mirror image of this and then try to decrease from here, and then wherever it lands, we take the mirror image back. Okay, so notice that this out of bound going problem is only here, which is if we multiply this v by this f, then it is possible that it will cross this one bound. But if we are trying to decrease it by dividing by this factor f, then it is never going to go below 0. Right, so in practice, it will look something like this. First, we take the mirror image, which is we take 1 minus v instead of v, and then we divide it by this factor, which is we try to decrement it, and then we take the mirror image again, which is subtract this entire quantity from 1. Right, so when we want to increment this value, we take the minimum of this 2. So that way we can ensure that it will never go beyond this one value. And when we want to decrement it, we can also take the similar approach, which is we take the maximum of either v by f or 1 minus v times f. So it is first taking the mirror image, then incrementing it by multiplying it with this factor f, and then finally taking the mirror image again by subtracting it from 1. So this 2 will increase the difficulty and this 2 will decrease the difficulty. To do a quick recap, in this video we saw how these LNS workers are scheduled inside this CP-SAT solvers. So typically, if you trigger the CP-SAT solver with 8 threads, then expect about 3 of them to only have LNS workers. So either LNS or LNS and local search, which is basically all types of re-entering type of workers. There is also an LNS only mode in CP-SAT solver, which is it will use all the threads in LNS mode, which is there are no full workers. So these LNS workers are kind of very successful inside this CP-SAT solver. So when you are using multiple threads, these LNS subsolvers contribute to a lot of solutions. Since there are like so many different types of neighborhoods, it diversifies the solution hunting process quite a lot. Right, so also we saw the different types of neighborhood generators. So there are generic ones that don't use any problem structure into account. There are neighborhood generators which use the variable or variable constraint graph information. There are some problem specific neighborhood generators as well. And of course, there are solution-induced neighborhood generators, which are typically found in MILP solvers, for example, RINS and RENS. Finally, we also saw how the time limit and the difficulty is adjusted based on whether that neighborhood generator or the LNS worker that is attached to that neighborhood generator, whether that found a solution or improved that solution or not. So I think that's all for this video. I hope you liked it. Do not forget to press the like button and subscribe if you haven't already. It helps me grow this channel. So I will see you in the next video.